We did try to start early. It was called the videos that were online. Yeah. All right, so let's start with section 3.6, the chain rule. Okay, this is a differentiation rule, and basically reads thus: if f is differentiable at the point u is equal to g of x, and g of x is differentiable at x, then we get this composite function, f of g of x. All right? Is also differentiable, and its derivative is f prime of g of x multiplied by g prime of x. So when we look at some expression that we want to take the derivative of, we look to see if it is a composite function, a function inside of a function, kind of like an onion or parfait. I think those are the most delicious desserts of all.
Is that a Shrek reference?
Yes. But anyway, think of a composite function as something being wrapped inside something else. If we see a function that looks like that, we are going to apply this thing called the chain rule. And the chain rule says you take the derivative of the outside function, that's our f function, and you leave the inside function the same. That's my g of x. So when I do the mantra for this, the derivative of the outside, leave the inside the same, and then multiply by the derivative of the inside function. Derivative of the outside, leave the inside the same, multiply by the derivative of the insides. Derivative of the outside, leave the inside the same, multiply by the derivative of the inside. Do you hear the mantra? Derivative of the outside, leave the inside the same, times the derivative of the inside. Okay, well, let's do an actual problem.
Times the what?
Times the derivative of the inside. Are you ready? Okay, so let's take a look at this function. The position function, s of t is equal to sine of 5t minus 3. And we want to find its velocity. Now we know what the derivative of sine is, but we only know it as the derivative of sine of x. Now we don't have sine of x or sine of t. We have something that's more complicated. Sine of 5t minus 3. All right? If we want to find the derivative function, the velocity function, we will do so by thinking of sine of 5t minus 3 as two functions. An outside function, the sine function, and then an inside function, 5t minus 3. And now we're ready to do the mantra. Derivative of the outside, leave the inside the same, multiply by the derivative of the inside. Here it goes. So the derivative of the outside function is cosine of t. The derivative of the inside function is 5. So we think about it as two functions, one inside the other. Sine on the outside, 5t minus 3 on the inside. Derivative of the outside is cosine, derivative of the inside is 5, and now let's put it all together. Okay? And if you want to think about this as the derivative of the two separate functions, the derivative of sine and the derivative of the u function, you might see something that's very nice going on there with the chain rule. The derivative of the outside is ds dt. The derivative of the inside, if we call it u, is du. Sorry. S is sine of u, right? And u is this thing that's going inside. So this the derivative of outside is ds du, and the derivative of the inside is du dt. These du's cancel and they leave us ds dt. So it's the derivative ds dt is cosine of u, cosine, leave the inside the same, times 5, and then to finish it off,
5 cosine 5t.
replace the u with what u is equal to, 5t minus 3. Now, this is again sort of showing it in longhand. But it shows you, this particular example is showing you why it works. It works symbolically with our ds du and our du dt. And you see how this answer matches that chain rule mantra. The derivative of the outside, there's my cosine. Leave the inside the same. Here's the derivative of the inside. So this is the chain rule. The derivative of the outside is the ds du. The derivative of the inside is the du dt. Let's try another one. Okay. Here's the same chain rule but in mantra form. Derivative of the outside, leave the inside the same. Multiply by the derivative of the inside. And this is going to give us the ability to do a whole lot more derivatives.
Yay.
That's right.
Are most of the composite functions we're going to do the sine and cosine, or t-trillion method?
Nope, we are not limited to how we can combine things. Sometimes it'll be sines and cosines. Sometimes they're going to be e's or logs. Sometimes they're going to be the square root function on the outside with a polynomial on the inside.
But it's not going to be like just 2 polynomials.
Why would we make that easy? If we're doing 2 polynomials, anyway. All right. So let's take a look at it again. Here's the inside-outside rule. If I'm taking the derivative of cosine 3 times x to the 4 minus 2, we declare the inside to be the 3 to the 4x, to the x to the 4th, 3x to the 4th minus 2. The outside function is cosine. So let's speak our way through the taking of that derivative using the chain rule. Derivative of the outside is negative sine, but you leave the inside the same. And then we say, what's the derivative of the inside? In this case, it's 12x to the third. There's the derivative of the inside. Now, if I use the same notation that we did on the first slide, what does this problem look like? Y is equal to cosine of u, but u is equal to 3x to the 4th minus 2. Derivative of y with respect to u is negative sine of u. Derivative of u with respect to x is 12x to the third. And what is dy dx? It's dy du. I want the du's to cancel, times du dx. And we end up getting what? Negative sine u times 12x cubed. And then this one is negative sine of, what's u?
3x to the 4th minus 2.
3x to the 4th minus 2 times 12x cubed. Now, between way number 1 and way number 2, which do you find easiest? Number one? Okay. Okay, I need you to be comfortable with both ways.
Yeah, all
And I
right, Phil.
especially want you to be comfortable with the idea that if I have dy du and du dx, I multiply them and I get dy dx.
Oh, you just made it go away.
Yeah. I don't know what you're talking about. No, what happens if I don't have a marker in my hand and I leave my finger on the screen for too long? So, but then it gives me an option to get it back. Are you okay? You ready for another example? All right, let's try for another example.
Among these raised my classmates.
Okay.
Do you want the derivative of the inside in front of the sign?
Here's what I do. Let me answer that question, and let me go through my thought process about that. Okay, my initial rewrite when I use the chain rule is exactly as the mantra states.
Okay.
Derivative of the outside, leave the inside the same. Derivative of the inside. Now, after you do that, there are certain norms that we follow, and those norms are typically the trigonometric functions are listed last. If we have a polynomial, the polynomial is listed from the highest order to the least order. Okay, we tend to put square roots last or after, so there's a pecking order in which we tend to write it. I don't say that the last chain always goes first. It's just a matter of the other norms that we use in terms of writing up things algebraically. Okay, so I would like you to write y is equal to the cube root of x sine x squared on your paper right now. And I would like you to think about this using a chain rule, and I would like you to work on it with your partners for just a second. Let me give you about 45 seconds.
So,
I can't say, you got a band? I'm not required to
what's
take
the derivative of...
What? All right? No, I got another idea. Tyler, you gentlemen,
This is the inside.
That's the inside. Okay.
Charles.
No, but it's
That's actually...
Charlie. The inside is. The inside is easy. It's sine sort of 2x. No, wait, no. Cosine 2x.
Yeah, when you cube root that, then
Paul, what are you doing? You abandoned? Will needs you.
I need some help on one thing. I was
Yeah.
really
You don't know
confused.
if Will has a beta
You need.
So we get cosine 2x.
That's right. That's right.
Okay.
Yeah.
So this is like 1 over 1.
Okay, so 1 over.
So it's like...
If you're getting a little bit stuck, it may be a good thing to remember that the cube root is the same thing as the power of,
So we get that.
to the power of 1/3. So what we're really in is in a power rule on the outside function. The outside function is a power rule. All right. Yeah, no, that's fine. Although sometimes, especially down the bottom, you see the 1/3 of everybody can keep reading. Either way it's fine. Yeah. Okay. Okay. Here we go with the first step of that. The derivative of the outside. Well, what is the outside function in this case? It's cube root of x.
It's the outside.
it the long way, my composite function is u to the 1/3 is my outside function. Sine x squared is my inside function. Are you okay with that? Those two composite together to get our y. So what am I taking the derivative of? What's my outside function? And there's my 1/3, and of course, u to the 1/3, and reduce the power by 1, and you get negative 2/3. What's my mantra there? Leave the inside. Now I'm going to multiply by the derivative of the inside. Well, sine of x squared is itself a composite function.
What?
I told you this is like an onion. This is
What
a
did you just say?
That's why it's a chain.
this function here is a composite function. U could be equal to sine of b,
Suppressing me.
and b is equal to
X squared.
x squared. So what we really have in this one is a double chain. Okay, it's dy du times du dv times dv dx. Woo! So here is dy du. Here is du dv. And there is dv dx, 2x. So what you think about doing, you take the derivative of the outside, leave the inside the same. The next thing itself could be a composite function. Peel off another layer. Take the derivative of the outside, leave its inside the same, and keep on doing it until you run out of composite functions.
Well, if you look at it, two
So when you get the first function, it's 1/3 sine x squared to the negative 2/3, and then the derivative of sine squared is cosine x squared.
Because the derivative of the outside
Okay, yeah,
is
and then when you're
and leave the
doing-
inside the same.
And then when you're doing the second composite
Hello.
function, it's the derivative. The derivative of sine is cosine, and then the inside function is x squared. Then you do it times the inside function, which is 2x.
Yep. You peel one layer, you peel the outside layer off, take the derivative of the inside. So derivative of the outside, leave the inside the same, then take the derivative of the inside. So in this case, in the first instance, sine x squared is the inside function. Derivative of the outside is cosine, leave the inside the same. Derivative of the outside there.
Okay.
Yes. This whole thing is the answer. Are you ready for another? Should we try another one?
Wait, just repeat our question. We're just at 2x from that.
Okay.
That 2x is the
Okay.
x squared, the derivative of x
Okay.
squared.
This is
Oh.
the derivative of the outside, but
Yeah.
leaving the inside the same. This is a composite function itself, so we take the derivative of the inside to get the 2x.
Okay. So it's like a derivative of a derivative.
It's like the,
Oh,
it's a,
man.
it's a three-chain,
Oh.
three-link chain.
Wait, what's the second?
That's the answer.
This is being here, taking this 2 and that 1/3 and getting a 2/3. Taking this x, bringing it forward. Remember we talked about, we tend to put the trig functions at the end of the line.
Wait, is this problem over?
That's the end of the problem.
No, they
Should we try another one?
Yes.
Okay.
Try another one. Ready? Paul, Josh. Are you ready? Let's do another one. Because this is just so much fun.
You're not having fun, you're crazy.
I guess I'm crazy.
I'm having
Let's
so
do
much fun.
g of t
Me and Jesse.
is equal to the tangent of 5 minus sine of 2t. Okay? You guys started with your partners.
Alright, so what's the answer?
Yes.
So outside this tan, so it's going to be tan u
We can do this?
Right, is that what we do again? Or what's that what we do?
Okay, so it says here
What's the difference of tan?
secant squared.
Yeah.
Outside. Right, and this
And then it's going to be this stays the same, 5 minus sine
now this is the outside
2t.
function.
So u would be 5 minus 2
What it is,
No, 5 minus 2 t is 5 minus 2
The derivative of this is negative cosine 2.
Oh, it's 2 shades, right?
We're doing this again. This becomes the
Oh,
outside.
we got that part right.
I'm going to guess it's 2 times 2.
Yeah, but what about this? It wouldn't be like negative cosine.
Yeah, I'm not sure.
Oh, did you take the X out there?
Oh, we broke it up into 3 things, so it's tan u.
Oh, it's just that.
What? Wouldn't it be just plain cosine because the derivative of sine? No.
Derivative of sine is cosine.
Yep, that's what I mean.
So the negative sign is staying there because
Yeah, I was thinking the negative. Yeah, I was thinking times 2. I did it right.
And then times 2.
yeah, those are all being multiplied together.
Yeah, why isn't the negative 2 be a little off?
So Katie said derivative of sine is just cosine. We were trying to change it to
Because I couldn't see the address.
because negative
It took me, I was on the other block literally for like 10 minutes.
Real smooth.
Fun stuff.
Wait, how'd you get the negative sign?
Putting the 2
Well,
Oh, times negative. Okay.
that negative sign right there.
The negative 2 is the negative cosine 2t times 2.
All those things are being multiplied together. So what I do at the end is I collect all those coefficients and put them all up in front.
Wait,
Wait, why did you multiply the negative cosine 2t times 2?
And then so that
Initially 2t.
there would be
Where's the t?
oh,
The derivative of 2t is 2.
So that's,
Don't you have to multiply it by the
oh, I get it.
size? It's really good.
I get this.
Like, no, I'm saying, I didn't. Take the derivative of that. Now this is the derivative.
Yeah,
Cosine is the outside,
And
like t is the inside.
she was on the wrong block. She's like, okay, I'm here. We're not gonna run. She's like, there's a scarecrow on the door. She says, there's a scarecrow on the door. I was like, he said on the tree. She goes, I'm gonna look. And she goes, this is the wrong address. This is 401. I'm like, it's 3803. You're not
Where is
401.
this outside?
This whole thing.
I was telling her everything you told me, and she's like, I remember you're the one who was like, it's past Morrison. So I go, past Morrison. I know. That's before yours.
Keep the inside the same.
That way, you're going. Yeah, wait, if you're going from my house, it's past Morrison. Yeah, but you can't come from Griffith Going south.
When you give directions, you're supposed to give them in terms of the person who's going.
You gotta like.
Not from you.
I love
Calc. Okay. Me too. I heart calc. Okay. So. Still feeling lost? Should we do another example? Okay. Now, there's two ways to explain it. Okay. I'm going to, for each step of the way, I'm going to put a green underline on the outside function. So, for the first step, there's my outside function, and there's its derivative. Everything that was here got plopped in there. Derivative of the outside, and the derivative of tangent is secant squared, right?
Yep.
Okay. Keep the inside the same. Now I'm going to underline the function I need to take the derivative of, right?
Yes.
So what is the derivative of 5 minus sine x 2t? Well, I don't even worry about the 5. That's a derivative of a constant, right? Let's just concentrate on the derivative of negative sine 2t. Constant multiplier, that stays there. The derivative of the sine function, the sine acts like the outside function now. Derivative of sine is cosine. So there's my derivative of the outside function. Leave the inside function the same. And then I say, I got an inside function, I got to take its derivative. The derivative of 2t is 2.
Okay, so sine in that case was the outside. Okay.
As I went from here to here, sine is the outside function, and 2t is the inside function. And then after I'm all done, I clean it up. Put my constants way out in front, so on and so forth. You want another problem? So take it through there. I want you to get confidence being outside and doing the inside. Yeah, Paul?
So, I mean, it would be fine though if we wrote it, like, we start off the whole equation secant squared instead of negative cosine 2t. Like, we can write the equation anyway.
Okay.
We just have to make it nice looking. Do we have to make it all nice looking?
You know, okay, here, I'm going to give you two other options of writing this. Okay, if you're having a hard time doing that way, I broke it down into 3 functions.
Well, I'm not saying that. I'm just saying, like, you know how you finish it off, you just summed it all up, put negative t cosine t squared? You know how, like, the steps we did it started off with secant squared, 5 minus. Can we just keep it like that, or should we, like, make it all nice like you did?
Well, I was trying to, 1, because I was running out of room this way, and 2, because I wanted you to see each time I pulled the wire off.
Yeah.
All right? Now, what if I did it this way? G, or dg with respect to u would have been secant squared, right?
Yep.
Du with respect to b would have been negative cosine of v, and then dv with respect to t is 2. And so dg, right, dg with respect to t would have been dg du times du dv times dv dt, which would have been secant squared of u times negative cosine of b times 2. Now, what's the difference between what I wrote here and what I got there?
You have to
Put in the U and V.
The u is need to be replaced, and the v needs to be replaced. Can you see it both ways? You like this better? Okay.
I like the whole one.
I like this one.
You can say green or blue.
All right.
I don't discriminate.
All right. How about we do one more problem? Watch out, I'm going to try to trick you.
Oh no.
Tricky tricks there.
The outside is the core. Maybe the core.
Okay, look at the new problem. Why is this problem more tricky than the other one?
It's got it to the fourth power.
This problem is
Because you can do this problem, and you will.
I think this will be the outside.
The tricky part begins with a P. The word is in power. The tricky part begins with the P, and I will bow down to the person who says it first. Who said product? Product.
I said product.
Okay, so this is the product rule first. This is the product rule first and foremost. Go.
You do that first.
Go.
Right? Okay.
what comes after.
You, Phil, if you want to turn around and work with Sarah and with
I mean, like.
Daniela.
We could use some help.
The product's going to do the derivative. First,
Oh.
alright. So back for that.
The second is
Times
This is actually.
I say we just put a 4 to all of them.
Do you and Will
2x4, that's
agree?
like, what, 8x,
Well,
something like.
why do I have these desks placed in pairs, Paul?
Because you want to do partner tests.
Every single test from now on.
I wish.
What if there's an odd number?
Well, that person will be left out. Not it. Those goes.
Then I get to be your partner.
I'll be your partner.
Peter can be my partner.
I already called.
Shiny.
Wait, what do you call it?
The car.
I don't think I got this right.
Wait a minute.
Oh.
Oh
Oh.
boy.
I got a squad. Look at that. I already got the first step down.
No, I got it up to the point.
What are you talking about?
Does that match what you guys were doing?
Yeah. Got it.
Really? Yeah? Okay.
Oh, I'm supposed to be checking it out first.
Okay, everyone look up at the board, double check to see if you're in the same path that I am.
Oh, I did this right. Oh, wait, no, I did it right.
Times 2. What's the outside function? To the fourth power. What's the inside function? 2x minus 5. So taking the derivative of the outside, bring the 4 down, reduce by 1, leave the inside the same. Take the derivative of the inside. There's your 2. We won't expand, but we will get all of our coefficients down to some. I don't take the 2 out. When I'm taking the derivative of this to the fourth power is my outside function. 2x minus 5 is my inside function. If I were taking this derivative using the other notation, it would be minus 5 is my inside. Derivative of this is 4u thirds. And the derivative of that is 2. So this part here shows up right there. The derivative of that shows up right there.
Okay.
The outside function was u cubed, u to the 4. So the derivative, what?
Why didn't you do it on the other side?
Well, I'm taking the derivative of x cubed. I think we got that one down already. This isn't a composite function. So there's no change.
Wait, so this had nothing to do with the change function?
No, I had to use the chain to get that part in. So Phil asked me, is that my final answer? No. My final answer is 8x cubed times 2x minus 5 to the third plus 3x squared times 2x minus 5 to the fourth.
Keep going. I got a really big answer.
No, I don't expand it from there. That's my final answer.
But I want to know
Wait,
if I got
Josh,
it right.
because his hand is up.
What if you factored an x squared times 2x times 5 quantity cubed?
You're likely to move away from the multiple choice answer if you do that.
Well, we got something smaller. Is that not
Oh.
right?
Let me take a look. Let me take a look.
What a showboat. And Nick was just saying.
You lost the power. Come on, everybody. You lost the power. You lost 60. Oh, you didn't.
Did you get it updated?
Take it. This is more likely. What I have is most likely. All right. You need another one?
Yeah, something like this.
One more. One more.
I might.
Find dy dx when y is equal to the square root of.
What's that first word? Fine.
Fine. Is that better?
Yeah.
Okay. So find dy dx when y is equal to the square root of tangent 5x.
Why'd you write fine so
I don't know why I do anything, Paul.
So it's the square root of u and u is
Why am I going to steal one of Caitlin's scoops?
Phone?
U is tan v.
Then try to do the or the script.
So it's going to be. So it should be 1/3. What? This is like
that's like u to the 1/2 power. And
That problem is so much easier to do.
So now it's 1/3.
Oh, okay.
Let's see.
That was the weirdest thing ever. That's my first.
Nick, if you talk to Emily, your partner,
Minus 1 roll.
something like that. So it would be like
Are you right? You're going to learn from?
Maybe like.
And she needs to do
I think it's that. Wait,
And then you lower it by 1. Keep the inside the same, lower it by 1. So 1 half minus 1 is like 1 half.
Okay, or just light.
No. When you take the derivative of tan, you neglect the derivative of tan.
Oh, okay. So is that that it?
Yep.
Okay. Alright.
Oh wait.
Calling your amazing I guess.
Oh, yeah.
Secant squared?
Yes.
Not at all.
SNL when they did.
Okay, I need
This is different notation than I used earlier, but these are the same idea. So maybe you also want to try to look at this and say, if my other two ways of presenting it don't make sense, try this next one.
And then oh, that's the inside of the
Again, I'd like to see a little bit more notation in your
And then you do plus.
Nope.
I was on the two. Oh, I didn't even like see it. I only F that when I was looking at the
I think so. Universally.
It was really. And he was like describing it. I'm like,
And then we did the six. So what's the
Take a finger? Yeah. What happens when you don't have fingers? Toe. Toe. It's worse than that.
If I'm going to use this other notation, completely, every single step used in one more chain rule.
I don't know how to work that out.
Okay, now if you're freaking out about them changing the negative 1/2, don't freak out. You got the right answer. It's just that remember, negative means it's in the bottom. 1/2 means it's the square root. So an alternate way of writing the answer, the correct answer that you have, is to take the square root and put it in the bottom.
So right.
So it would be what?
What's the
5
wait?
Well,
What's
you
the
can
answer
at
of
least
that?
do it in the bottom.
and squared.
Okay, that one I understand.
You'd be surprised how
got that
often
one
you
too.
see a square root in the bottom
Why is there
in this class. You know, it's really because you got drilled into you. Rationalize the denominator, and then we go ahead and we break those rules.
Wait a minute.
Yeah.
It's kind of like creative writing. You learn all the rules of grammar so you can learn how to break them in new and creative ways.
Is that 5x to the first?
Yeah. No.
No, it's the square root of tangent of x.
I was closing off my square root.
Is that what you're supposed to? Oh.
I was trying to show where the square root ended.
Yeah, I remember 2 times that as a whole.
So I put a little.
Oh, okay.
All right.
So the 5/2.
One more example. Yeah, I'm gonna be.
Okay.
But I'm here every month. All right. What do we got? 6 minutes left. Not 6 minutes left. How much do we have? 9 minutes. All right. I need to go on. All right. But I intend to put lots of your homework problems in movie form up on the website later tonight. All right. Now, we've got one more situation. And that is when we have a curve that's made up of 2 parametric equations, parameterized curves. All right? We also have the need to be able to find the derivatives based on this. And what's going on is we kind of know that parameterized curves can be curves that are really crazy. They don't look like functions. They fail the vertical line test. They fail the horizontal line test. All those kinds of things. But we still can use the chain rule to find out the slopes on curves that are given parametrically. Okay, so let's start with this idea that we have a parameterized curve. It's made up of two functions, x of t and y of t. T is our independent variable, and now x and y are dependent on our choice of t. First of all, the derivative of that curve, meaning the slope at some location on that curve, is only existing when both x and y are both differentiable at the point that we're going to take the derivative. So if either derivative, either the x prime or the y prime don't exist, we say that that curve is not differentiable at that point. Now, if I want to find the slope of the slope at a point on that curve, I'm looking for dy dx. If I'm trying to find the slope of a curve, I'm trying to find a change in y with respect to a change in x. But the new monkey wrench in this is that x is not, or y is not a function of x. Y is a function of t, and x is a function of t. So how are we going to find dy dx? Well, we're going to take dy dt, because that's easy to find, because y is a function of t, and we're going to find dx dt, which is easy to find because x is a function of t, and when I divide dy dt by dx dt, you know what I get? Dy dx. Or another way of saying this, you know what I get when I take dy dt and divide by dx dt? Well, dx dt, dividing by that fraction is like multiplying by its reciprocal. What does that look like? The chain rule. Again.
Oh boy. Big Mama.
No, it's not Big Mama. All right, so let's go ahead and let's do an example where we find dy dx from a parametric situation. By the way, this is just what I just said, so don't worry about that. Oh, I'm sorry. I'm sorry. I need a blank slate. All right, so let's say that we have parametrically x is equal to secant of t and y is equal to the tangent of t. There's my curve parametrically, and we're talking about this while t is between negative pi over 2 and pi over 2. And my question is, what is dy dx? So it's going to be dy dt all over dx dt. What is dy dt?
Should we write it as dy dt times dt dx?
You could. But what you're going to find, I did that flip over so you can see those dt's cancel. I'm doing this because when we take those derivatives, typically they're just very simple expressions anyway. So it's easier to say, I can read dy dt off secant squared. I can read the derivative of that off, and that is secant tangent.
And then
So we end up with secant over tangent, which is 1 over cosine t times sine on the bottom and cosine on the top. We end up with 1 over sine, which is cosecant t.
that was too much.
1 over cos.
Okay.
I think we use everything except for cosine.
What's the radiation out? Radiation.
Okay. Read the next thing that I wrote in English, please.
dy dx is t is pi over
Okay.
The
Let's,
derivative of y in respect to x when t equals pi over 4.
okay, let's read that vertical line as when.
When?
Okay.
When t equals.
When t equals pi over 4.
The derivative of y in respect to x when t is equal to pi over 4.
Okay. Okay, or we could say the slope of the curve when t is equal to pi over 4, that can be read as a slope as well. And we get what? Cosecant of pi over 4. Cosecant of pi over 4.
1 over sine of pi over 4.
1 over sine of pi over 4.
1 over sine of pi. No, I don't want decimals.
Pi over 2. No, never mind.
There's not a pi in any of these.
Root 2 is 1. Root 2 is 1. Definitely 1.
Square root of 3
is the answer.
Okay, ready? You're struggling with this. Let me help you. Draw a reference triangle. 1, 1, root 2. There's my 45, 45, 90 reference triangle. Here's my pi over 4 angle. Cosecant is hypotenuse over opposite. Square root of 2. Okay, let's confirm that. Let's confirm that. Did I already give you your assignment? Because we're going to run out of time. All right, I'm going to give you your assignment. Hold on. And then I'm going to confirm that answer. Okay. Whoa.
1.35.
That's not right.
No, 51 to 65 high.
It's, no, what it is, no, it's 1 through 65 odd.
Oh, God. Mr. Fedor.
Hold on. Let's try this.
These problems go quick. Emily, you're probably going to do this exam.
3.6, right? 3.6.
3.6.
Wait,
There we go.
the exam took a long time though.
I think what it said was 60 through 65.
I'm pretty sure it said every other.
All right.
I have dyslexia, so
I need to show you. You're going to want to see this last thing on the calculator before you leave. You really are.
I want to see it.
Oh.
Come on, quick, do it.
I really want to see it.
Speed count. Speed count.
Going into parametric mode.
You know what?
Cosine. Tangent.
I'll show up for like 2 seconds.
Cube. Normal. Here's my graph. Second count. I want d, y, dx. D is equal to pi over 4. Pi and right. So didn't go to chalk.
He's probably not awake yet, but I'm going to pick him up now because we're going to Ernie's. And I think he's